This session is about motion, which is in paper 2 and is for combined and triple science. We looked at scalars and vectors earlier, but here is another example. Distance is how far an object moves and is a scalar quantity, but displacement says how far the object moves in a straight line and is a vector quantity. Speed tells us how fast an object is moving, and it doesn't involve direction, and it's a scalar quantity. But the speed of a moving object is constantly changing. We need to know some types of speeds, so we should know some typical values such as walking, which is 1.5 meters per second, running 3 meters per second, and cycling 6 meters per second. Another one you should be familiar with is the speed of sound in air, which is 330 meters per second. There's an equation for speed that you need to know. Speed equals distance divided by time. Speed is measured in meters per second, distance in meters, and time is measured in seconds. The velocity of an object is the speed in a given direction, so velocity is a vector quantity. We need to be able to draw distance-time graphs, and the gradient of a distance-time graph gives the speed of the object. Have a look at these graphs and see if you can decide what the object is doing. In diagram A, the distance isn't changing with time. This means the object is not moving. If you look at B, the distance is increasing, but very evenly, so the same amount every second. So this object is moving at constant speed. What about diagram C? Here, the distance is decreasing at a regular rate every second. So it's going back to where it started, but it's doing it at a constant speed. At D, the gradient or slope of the graph is increasing. The gradient tells us the speed of the object, so this object is accelerating. E is doing the opposite. Its gradient is decreasing, so it's decelerating. How does diagram F compare with B? It's still moving at a constant speed, but it's slower than B. Another way to draw a motion graph is to draw a velocity time graph. In this, there are two things we can find out. The gradient gives us the acceleration, and the area under a velocity time graph tells us the distance travelled. How are these objects moving? They're very similar to the diagrams we looked at a minute ago, but this time there is speed or velocity on the y-axis. So in A, the speed is not changing. This means it's going at constant speed. What about B? Its speed or velocity is increasing very regularly every second. This means it's accelerating, but it's accelerating at a very even pace. So it's accelerating at a constant rate. Make sure you use the word rate rather than speed here, otherwise it will cause some confusion. It's accelerating at a constant rate. What do you think C is doing? C is decelerating at a constant rate. Look at D. At D, the gradient is increasing, so its acceleration is getting faster and faster. It's accelerating slowly at first and then faster. And E is the opposite. It's accelerating quickly at first and then more slowly. How does F compare with B? It's still accelerating at a constant rate, but its rate is less than B. Acceleration. Acceleration is speeding up or slowing down. So it's a change in velocity, and it's how quickly it's doing it. So it's over the time taken. We can write this as A equals V minus U over T. A stands for acceleration. This is in meters per second squared. There's often a mark for remembering this unit. V is the final velocity in meters per second, U is the start velocity in meters per second, and t is the time it takes, measured in seconds. This is an equation that you need to learn. But there is another equation we can use, but this one's on the sheet. It's the final velocity squared minus the start velocity squared, and it's equal to 2 times the acceleration times the distance travelled. V squared minus u squared equals 2as. You'll be less familiar with this equation, but it is worth remembering that it's on the sheet in case you need it. Again, a is acceleration in meters per second squared. V is the final velocity in meters per second. U is the start velocity in meters per second. T is the time, measured in seconds. And s is the distance travelled, measured in meters. You need to remember which is which for Newton's laws. And Newton's first law talks about balanced forces. This is when the forces are equal in size but opposite in direction. We need to draw them so they look equal in size as well. The resultant force would then be 0. In this situation, the object will do one of two things. If it's stationary, it'll stay stationary, not moving. But if it's already moving, it'll continue to move at constant speed in the same direction, so the same velocity. The tendency of an object to continue in its state of rest or motion is called inertia, and we need to know this term, inertia. Newton's second law talks about unbalanced forces. This is when one of the forces is bigger than the other, so you get a resultant force. There's a required practical linked with this that you need to know about too. And the equation is that the resultant force is equal to the mass times the acceleration. F equals ma. Now the force is the resultant force measured in newtons. The mass is called the inertial mass, which is measured in kilograms. And a is the acceleration, again measured in meters per second squared. You must learn this equation. Inertial mass is the measure of how difficult it is to change the velocity of an object, and it is defined as the ratio of force over acceleration. So Newton's third law looks at forces acting on different objects. Up to now with the first and second law, we only looked at the forces acting on one object, the same object, to see how it would move. But this is all about one object putting a force on another, which puts an equal and opposite force back. For example, the person here is pushing against the wall, and the wall is pushing back on the person. An object falling through a fluid, such as a liquid or a gas, initially accelerates due to the force of gravity. But eventually the resultant force will become 0. This is because as it gets faster, the resistant force, or air resistance or drag force, will increase. The drag force depends on the velocity, so the bigger the velocity, the bigger the drag force, and this means it eventually balances the weight of the object. You can see from the 3 diagrams at the bottom, at the beginning it's just the weight acting down. Then in the second middle picture, the weight is bigger than the drag force. And then finally in the picture on the right, the weight is equal and opposite to the drag force. This gives us the velocity time graph on the right hand side. The initial acceleration will be 9.8 meters per second squared, but as the drag force increases, as the velocity increases, the acceleration gets less and less, so the graph starts curving over. Finally, the weight is equal to the drag force, and the line is horizontal, and the object falls at terminal velocity. Stopping distance is equal to the thinking distance plus the braking distance. Is the overall distance it takes a driver to stop when they see a hazard. The braking distance will increase with speed and the thinking distance will increase with speed, so the overall stopping distance also increases with speed. You can see a diagram of how the stopping distance is equal to the thinking and the braking distance added together. And in the graph at the bottom, you can see that during a person's reaction time, the velocity of the car doesn't change. It's while they're sort of thinking about putting their foot on the brake. So they travel at constant velocity at first, and then the velocity decreases at a constant rate when they are braking. Thinking distance. This is the distance the car travels during the driver's reaction time. Reaction times are about 0.2 to 0.9 seconds, and this can be affected by tiredness, drugs, and alcohol. Distractions also affect the driver's ability to react. Braking distance is the distance the car travels while it's braking, so under the braking force. And the braking distance of a vehicle can be affected by the road conditions, such as wet or icy conditions, and poor condition of the vehicle. This is really limited to the vehicle's brakes or tyres. Braking distance and work done. So when your car is braking, what you're actually doing is changing the kinetic energy of the car to other forms, such as heat in the brakes. So the work done is equal to the energy change, so it's equal to the kinetic energy lost. And the braking force times the distance moved, because work done is equal to force times distance. The greater the speed of a vehicle, the more kinetic energy it has, so the bigger the braking force needed to stop it in a certain distance.